Welcome back. In this lecture, we're going to be learning about some important terms and definitions that will be very important for the rest of this year. Speed, velocity, acceleration, and momentum. Our first important definition is average velocity. Average velocity is defined quite simply as the change in the position of an object divided by the change in time. You may notice that this in the numerator is what we have already defined as a relative position vector, which is sometimes written like this, where the delta means change in. So change in position divided by change in time. This is a vector quantity, and because the relative position vector is also a vector, we can see that the average velocity here, if we show this graphically, it's always going to be in the same direction as the change in position. Remember that because velocity is a vector, it does have two components that make it up. It has a magnitude and it has a direction. As we've said earlier, the magnitude of average velocity is what we call average speed. So although in everyday English the words speed and the words velocity are used interchangeably, they are not exactly the same thing when we're in physics. Velocity includes both speed and the direction, whereas speed is just a number. Let's look at a couple of examples of calculating the average velocity. Example number 1. Consider a bee in flight at time t initial equals 15.0 seconds after 9 a.m. The bee's position vector was 240. Later, at a final time of 15.1 seconds after 9 a.m., the bee's position vector was 3.50. So what was the average velocity of the bee during the time interval? Remember that average velocity is simply the change in position divided by the change in time. So in order to calculate the average velocity, we need to know both of these things. Let's look at calculating the average position first. The average position, the change in position, I should have said, is the final position minus the initial position. So the final position here is 3.50 meters, minus the initial position is 240 meters. That gives you a change in position, if we subtract these two, of 1 negative 0.50. We also need to look at the problem and determine what the change in time is. So we know the change in position, the change in time, it goes from 15.0 seconds to 15.1 seconds. So the change in time, therefore, is equal to 15.1 minus 15.0, which is 0.1 seconds. Now we're ready to find the average velocity. To find the average velocity, we're going to divide these two quantities. The change in position divided by the change in time. Let's write the answer down here a little bit. So our average velocity then will be 10, negative 5, and 0. And the units are meters per second because our units of distance were meters and time are seconds. While there are many units that you can use for average velocity, meters per second is the standard one that we will use primarily throughout this whole class. Now, this is one way to write this vector, but remember you can also write this in terms of the magnitude and the unit vector. So let's practice doing that again. To find the magnitude of the vector, we simply take the square root of each of the terms squared. Gives you a total magnitude of 11.18 meters per second. And then to find the unit vector, with the hat to show that we're talking about the unit vector, we take the original vector and divide by the magnitude. To get these three components. So finally, we can write the average velocity in terms of a magnitude times a unit vector. And this will be our final answer. Let's look at one other example. We're going to go through this one quickly because it's pretty much repeating the same thing as in the previous example. So once again, we want to first find the change in position, the relative position vector, by subtracting the final position minus the initial position. To give you a change in position of 4, minus 5, and 6. We also need the change in time, which is the same. The final time minus the initial time, which is 0.5 seconds. So dividing these two things to give you the average velocity, gives you an average velocity of 8 minus 10, 12 meters per second. Now once again, this is one way to write this vector. We can also write it in the form of a magnitude and a direction. So let's do that. If you calculate the magnitude, you should get 17.55 meters per second. I'll leave that for you to check and make sure that you can get the same answer. And then to find the unit vector, you should get 0.456, negative 0.570, and 0.684. Again, pause the video if you need to and check and make sure that you can actually get the same answer that I did here. Finally, we can rewrite the average velocity as the magnitude, 17.55 meters per second, times the unit vector. Right, so each of these are valid ways to record the average velocity. What would not be a valid way is just to say 17.55, because that would be what? Average speed, not average velocity. They're not the same thing exactly. Now, let's look at how we can use this idea of average velocity to actually predict the future. That's kind of where we're going with this. One of the big goals of physics is to predict what's going to happen in the future, even though we may not have seen it happen yet, based on what we've observed happening in the past. So, remember that our average velocity equation said the change in position divided by the change in time. Well, we can rearrange this equation to solve for the final position. So say you know the average velocity and you know the initial position and the time, you can rearrange that to get it in this form. So that now we have a way to predict what the final position of an object is going to be if we know what the velocity is. And this is assuming that it's moving with the same velocity the whole time. We're going to look at situations later where the velocity is changing, and then we can calculate that a little bit differently. But first, let's look at a couple of examples of using this position update equation. So in this first example, the initial time is 12.18 seconds after 1:30, and the position vector is 28 minus 12. The ball's velocity at that moment is 9 minus 46 meters per second, and at the final time is 12.21 seconds after 1:30. We want to know where will the ball be, assuming that the velocity is constant or nearly constant during that time interval. So again, we can use our rearranged form of the equation for average velocity to find that. Now, I wouldn't recommend that you try to memorize this equation as something different, because it is simply just a rearrangement of the definition of average velocity. So if you can't just remember it offhand, you can always get back to this equation as long as you know what average velocity is. In this, the initial position is 28 minus 12. We were given the average velocity, of 9 minus 46 meters per second, and we're going to multiply that times the time that it actually traveled, or the change in time, which was 12.21 seconds minus 12.18 seconds, or 0.03 seconds. So adding these two things together should give you a final position of 20.27, 7.88, and negative 11.82 meters. So now, even though maybe we hadn't seen that happen yet, we can actually predict accurately where this ball is going to be sometime in the future. Let's look at another example. Very similar problem. Once again, we're going to use the position update form of our average velocity equation. Right? We want to find the final position. In this case, given that the initial position is 0, because it says passes the origin. So when you see origin, you should immediately think these are the coordinates of the origin. So that's where it is at 9 seconds. So we're going to start with an initial position of 0, and we're going to add to that the velocity, the average velocity during the time, times the time interval. Now the time interval would be 0.7 seconds. It's 9.7 minus 9 to give you 0.7 seconds. And that's going to give us a final position in coordinate form of 2.1 times 10 to the 5th, 1.4 times 10 to the 5th, and 2.8 times 10 to the 5th meters. So far, everything we've done in this lecture has dealt with average velocity, which just takes 2 points, subtracts them, divided by the time interval to get what the average velocity is over a certain time. That works pretty well when you have things that are moving with a constant velocity. If the velocity is not changing, then the average is going to be a good approximation of what the velocity is at any moment. But that's not always true for every situation. In some cases, the velocity actually is changing, and in those cases the average velocity may not be a good measurement of the velocity at any point. Take, for example, this case. This is the graph of position versus time. Remember that on a position versus time graph, the slope of that graph is going to tell you what the velocity is. Well, in this case you have a changing slope, so we know right away that the velocity is not constant. To find the average velocity, what we would do is we would take 2 points here and here, right? We could find the average velocity between B and E by saying the position at E minus the position at B divided by the time it took to go from B to E. Now that would give us an average, and it would be the slope of this line here, right? But does that mean that the velocity was that during this whole time? Clearly not. In fact, at this point here, the object even changed direction. So the object was going one way, it stopped, and it turned around and went the other way. So the average velocity in no way really represents what the velocity was at every second. So how do we go about figuring out what the velocity is at a certain instant in time? This is what we call the instantaneous velocity. It's the velocity at a single instant in time. So not an average over a longer time period. Well, to get there, we can start with the idea of average. Imagine that you take smaller and smaller and smaller averages as we see here. First, we have an average from B to E, right? Then we can take an average from B to D, then from B to C, and you can see that the average from B to C actually does get pretty close to approximating what the actual speed is during that whole time. We can take this even further and think about what would happen if you had an infinitely small time interval. So the limit as delta t goes to 0. Of delta r over delta t. When that happens, this actually turns into a derivative. So we can write this and say that the instantaneous velocity is the derivative of the position. If you have a function that describes how the position is changing over time, and sometimes we will, you can find the derivative of that to actually give you what the velocity is at any moment in time. Not an average, but an instantaneous velocity. Another important definition that we will need to know now is acceleration. So acceleration is defined as the rate of change of velocity. Average acceleration, again, is the change in velocity divided by the change in time over a time interval, just like average velocity is the change in position over the change in time. If we take the limit as this approaches 0 once again, then we see that the average acceleration is simply the derivative of the velocity, which means that it is the second derivative of the position function. So we can go back and forth between acceleration, velocity, and position just using a little calculus. Now, this is a vector. So when you take a derivative of a vector, it is not as simple as simply taking a derivative of a scalar number. There will actually be two components of this derivative. So if you were to take the derivative of the acceleration, you would have to use the chain rule. We would say the derivative of the magnitude times the unit vector, because remember this is made up of a magnitude and a unit vector, plus the magnitude times the derivative of the unit vector. This is a part of acceleration that deals with changes in magnitude, so changes in speed. This is a part that deals with changes in direction. Both of those are forms of acceleration. We call those two different types of acceleration tangential and radial. So tangential acceleration occurs when you have a change in speed, where radial acceleration occurs when you have a change in direction. This is sometimes called centripetal acceleration as well, because it's acceleration of something that's turning or going in a circle. Let's look at an example, a couple of examples here of calculating acceleration then. First, we'll look at an average acceleration, and then we'll do an instantaneous one. And this problem says powerful sports cars can go from 0 to 25 meters per second in 5 seconds. What is the magnitude of the average acceleration in this case? And how does this compare to the acceleration of gravity, of a rock falling? So, to find the average acceleration, we're going to take the final velocity, which is 2500, and we're going to subtract the initial velocity. So how did I know that we put zeros for the other? We're making a few assumptions here. We're assuming that the car is going in a straight line on this track. It's going from 0 to 25 miles per hour, just in one direction. If it was turning at the same time, that would complicate matters. And that would make, you would have two different kinds of acceleration there. So we're making that assumption that we're just dealing with one-dimensional motion right here. Now to find the acceleration, we're going to divide this by 5 seconds to get how quickly does it change over time. So the acceleration here is 5, 0, 0 meters per second. How does this compare to the acceleration of a rock? Well, the acceleration due to gravity is approximately 9.8 or close to 10 meters per second squared. So this is 5, should say this should be squared as well. This is 5 meters per second squared, so it's a little bit less than the acceleration due to gravity. Okay, next let's look at an example where we do have to use some calculus. In this case, we're given a function that gives us the 3 different components of the position of the object at any time. We want to find what's the instantaneous velocity at any time, so time t just means a function for it, and then the acceleration at time t, and then we want to plug in a time of 0 and see to get some actual numbers. So if we have it in component form like this, to find the instantaneous velocity, we're going to take the derivative of the instantaneous position. We're going to differentiate each of these 3 terms separately, right? So the x component will be the derivative of 3 plus 5t, which is simply 5. The y component will be the derivative of 4t squared, which is 8t. And the z component will be the derivative of 2t minus 6t cubed, which is 2 minus 18t squared. Now, if we want to go on and find the acceleration, we're going to do this one more time. Right now, we're going to look at the velocity function here. Derivative of 5 is simply 0. The derivative of 8t is 8. And the derivative of 2 minus 18t squared is minus 36t. Now we have functions that allow us to calculate the velocity and the acceleration at any point. So we can plug in 0 to get what is the velocity at t equals 0. We're going to plug in 0 for all instances of t here, so we would get 5, 0, 2. And we can do the same thing for the acceleration. 0, 8, 0. All I'm doing is taking 0, plugging it into these equations and these equations for velocity and acceleration respectively. Finally, the last and maybe most important term that we're going to define in this lecture is momentum. Momentum is going to be something that we deal with throughout the whole year. The approximate definition of momentum, and at the end of the lecture today you'll see why it's considered approximate and not exact, is that momentum is equal to m times v. The symbol for momentum is p. I'm not really sure why that is, but that's what it is. M stands for the mass of an object, v stands for its velocity. So writing this out in words, we would say that momentum of an object equals mass times velocity. Now, because velocity is a vector, momentum is also going to be a vector. Mass is a scalar, so I'm multiplying a scalar times a vector to get a new vector. Now that we know something about momentum, we can restate Newton's first law in another form, in a simpler form. And this is the way that Newton originally said it. He said to change an object's momentum, a force must be applied. So if you see an object that its momentum is not changing, then you know that there's no net force acting on the object. Let's look at an example problem of calculating momentum. In this case, we have a problem of a tennis ball bouncing off of a wall. So the first thing we want to do is try to draw a picture. I'm a strong believer in drawing pictures of everything in physics. Sometimes if you have no idea what to do, just sitting down and drawing a picture of it will help clarify the situation, and it will help show you what you need to do. So pictures, diagrams, these are tools that you should always get in the habit of using as much as possible. Let's start off with the ball moving this way. Right. It's going to have some initial momentum. Right? It's going to travel to the wall, it's going to hit the wall, and it's going to bounce back off with some final momentum. Well, let's calculate what that momentum is. The mass is 58 grams. Typically, when we calculate momentum, we always want to use kilograms. So the first thing we would want to do is convert 58 grams to 0.058 kilograms. Then we're going to multiply this times the velocity at which it was headed toward the wall to give us an initial momentum of 2.900 kilogram meters per second. They may have also noticed here, momentum doesn't have its own designated unit, like a lot of other things. There is no derived unit. So for momentum, we're just going to write down kilogram times meter per second. Those are the units of momentum. Now the problem says that when the ball bounces back, it has nearly the same speed in the opposite direction. So the only thing that changes here is the direction. Now the second thing says, what is the change in momentum? This is a problem that's trickier than it seems, because a lot of times the tendency is for people to look at this and say, okay, well it has the same momentum when it hit and when it came back. So therefore the change in momentum is 0. But that is incorrect, because momentum is a vector, it has a direction. So if we actually think about this and we subtract the final momentum minus the initial momentum, remember the final momentum is negative, the initial momentum was positive. So when we subtract these two things from each other, we get a change in momentum that is double momentum. So not only does the ball have to stop, it has to turn around and go in the other direction. So that's a change in momentum that's double the initial or the final momentum. So when something bounces off something, it has a big change in momentum. Change in momentum is not 0, because you always have to be careful to keep track of the direction of the momentum. It's very important. Alright, next example. This is where we have something actually not going in a straight line. The planet Mars has a mass of 6.4 times 10 to the 24th kilograms, and it travels in a nearly circular orbit around the Sun, as shown in this diagram here. It's also on page 27 in your book. When Mars is at location A, we know the velocity is 0, minus 2.5 times 10 to the 4th meters per second. When it reaches location B, the planet's velocity is minus 2.5 times 10 to the 4th meters per second in the x direction, 0, 0. So we're looking down on the orbit from above, the north poles of the Sun and Mars. Positive x is to the right, and negative z is kind of down the page. And positive z, is down the page. What is the change in momentum of Mars between locations A and B? This is maybe not quite as simple as before, because they're in different directions. So once again, what we need to do is figure out what are the initial and final momentum of Mars at point A and point B, and then subtract those two. So momentum is mass times velocity. We have the mass times the velocity. When we multiply those two things together, you get a momentum of 0, 0 minus 1.6 times 10 to the 28. And again, kilogram meters per second are the units. Now we can do the same thing for the final momentum. And you're going to get negative 1.6 times 10 to the 28, 0, 0. So that the change in momentum is the difference between these two. So subtracting the final momentum minus the initial momentum. Subtracting those two gives you minus 1.6 times 10 to the 28 plus 1.6 times 10 to the 28, 0. So we can do this numerically. It's sometimes also a good idea to try to show the change in momentum, show the momentum just graphically, so you kind of think about what's happening and don't always just rely on numbers. So if we go down to points C and D here, what direction would the momentum be at point C, right? If we notice a pattern here, the momentum is always tangent to the path. Alright, so if the Mars is moving around this way, it's going around this, and when it gets here, the momentum is straight ahead. When it gets up here, the momentum is this way. So when it gets to C, what direction would the momentum be? Alright, this way. When it gets to D, it's going to be rotated a little bit that way. Does everybody see how that works? Alright. A couple of other questions I wanted to ask here. Is there a force acting on Mars? We see Mars going in a circle, but it's not speeding up or slowing down. So is there a force actually acting on it? Yes, there is. How can you tell that there's a force acting on Mars, right? Because it's moving in a circle. It's changing direction. Now, a trickier question, is Mars exerting a force on the Sun? The answer to this is also yes. We'll talk more about this later. But the third law of motion says that all forces occur in pairs. So it's impossible for Mars to be pulling on the Sun, or I'm sorry, it's impossible for the Sun to be pulling on Mars without Mars also pulling on the Sun. So how come the Sun is not moving due to the Mars pulling on it? Well, in fact, it is a little bit. But we don't notice it as much because the Sun is just so much bigger. It has a much bigger mass, so the force is not as noticeable. We'll come back to that idea later, but I did want to introduce it just a little bit here. Next, just as we used before, we updated the position using velocity. Since momentum is related to velocity, we can also use momentum to update the position. Remember this from just a few minutes ago? Okay. Well, we know now that we can write momentum as mass times velocity. So we can write this average velocity as the momentum divided by the mass. So that means we can change our position update equation. And if we happen to know the momentum instead of the velocity directly, we can always find the velocity by dividing by the mass and then continue on as usual. So let's look at one example of this before we move on to talking about momentum at high speeds. This example says an ice skater whose mass is 50 kilograms moves with a constant momentum of 400, 0, 300. At a particular instant in her skating program, she passes location 003. What was her location at a time 3 seconds earlier? So in this case, instead of actually solving for RF, we're trying to find the initial position. We know the final and we want to find the initial. So what we would do is rearrange this equation slightly and say it's final position minus. Now we're going backwards in time. All right. Plugging in the numbers that we have, we can find what the initial position is. Now, we don't have the average velocity. What we do have is momentum. We can divide that by the mass. and multiply by the time, which was 3 seconds, to find where the skater actually was 3 seconds in the past. And you would find that she was at minus 24, 0, minus 15 meters. So it goes both ways. We can use momentum, we can use velocity, we can find the initial, we can find the final. We can do a lot of things with this one basic equation. The last thing I'm going to talk about in this lecture is what happens when you go at very high speeds. And by very high speeds, I mean near the speed of light. So near the speed of light, momentum actually can change. This is due to, or this is explained by Einstein's special theory of relativity. Which says that things change. The speed, the mass actually changes when you start going very near the speed of light, and momentum itself actually changes. We have to multiply our standard way to calculate momentum, m times v, by this new factor, which is called gamma. Now, I've shown you some common examples of what gamma is, and you notice that it is not until you get relatively close to the speed of light, kind of here, that you start to deviate very much away from 1. The speed of light is about 3 times 10 to the 8th meters per second. So how do we actually calculate gamma? For any speed of light, gamma is defined in this way. It's 1 divided by the square root of 1 minus the magnitude of velocity that the object is moving at divided by the speed of light squared. So as long as the velocity is much smaller than the speed of light, this term is very small, and the gamma term is essentially 1 divided by 1, which stays 1. It's only when the velocity becomes near the speed of light that it starts to be maybe a little bit of a problem, and you may have to actually use this. Let's finish today by looking at one more example of how to calculate the momentum when something is going fairly near the speed of light. So, to calculate gamma in this case, the first thing that we're going to need to know is what is the magnitude of the velocity. I won't go through all the steps of that. Hopefully by now you feel a little bit more comfortable with that, but I encourage you to pause the video and try to do it yourself and make sure that you can get this answer. But you should get 3.7 times 10 to the 7th meters per second. Now, we're going to use that to find what gamma is. In this case, our speed was 3.7 times 10 to the 7th. Gamma is 3 times 10 to, the speed of light is 3 times 10 to the 8th. We're going to square this whole term, take the square root of the denominator, and then divide and find, say, 1 divided by that number. This gives us a factor of gamma of 1.007. So to calculate the momentum, because this is somewhat near the speed of light, we would need to actually multiply our typical MV calculation by that factor gamma. So we would have 1.007, then the mass, then the velocity. That's going to give you a momentum of 3.4 times 10 to the minus 20, 1.7 times 10 to the minus 20, and minus 5.1 times 10 to the minus 20 kilogram meters per second. Now once again, what's the momentum? or what's the magnitude of the momentum? You can find that just like we found every other magnitude by taking the square root of each of these terms squared and added together. That's going to give you a magnitude of 6.4 times 10 to the minus 20 kilogram meters per second. So when do you need to do this? I know that you don't want to, every single time you're calculating momentum, go through this whole process to calculate gamma. You can use P equals mv in almost every situation. Whenever v is not near the speed of light, then that means that the velocity is much less than the speed of light. Gamma is approximately equal to 1, as we showed in this table. So for 99% of the situations we're going to encounter in this class, we're just going to use this standard form of our momentum equation. This is what we call the approximate equation for momentum, as I said in the very beginning, and the reason it's approximate is because it doesn't exactly calculate the momentum in all situations, but for most of the time, except for a few instances, it's going to be sufficient for our needs.